Hello. This talk will be on truly perfect samplers for data streams and sliding windows by Raj Jairam, David Woodruff, and Samson So. So a lot of us are familiar with sampling. It's a great way to obtain representative statistics for an overall population when we don't have access to individual members of the population. So for example, let's suppose that we want to test a student's knowledge over some subject without asking every single detail about this subject. Well, a frequent way to do this is to use an exam. And here we'll include representative questions on the topic in the exam, and that will be used to assess a student's overall knowledge in the subject. Sampling is also used in the form of census inquiries, where we want to determine statistics of a population based on a number of responses from a small subset of the population. And this is similarly done in both exit polls and surveys. But one can also think of a situation where inspection can be viewed as a periodic sample over time of, say, let's say a restaurant's quality in terms of meeting standards that are required by, say, the FDA. Speaking of the FDA, another way that sampling is often used by, let's say, drug and pharmaceutical companies is to select a number of members from the overall population to test some of their products. And hopefully the results from the test will be representative of how these drugs or products will behave on the overall population. So good things can happen when sampling is done right, but there are also famous examples of when sampling is done wrong. For example, the famous survivorship bias and other forms of sampling bias. So in this talk, we'll focus on the streaming model, where the input is elements of an underlying dataset S, which arrive sequentially, and the goal is to sample some member of S according to some given function. But of course, we would like to do this using space that's sublinear in the size of the input S. For example, we'll consider the instance where the streams S induces a frequency vector F, and we'll let the Fi be the frequency of element I, which is how often it appears. So suppose we have the stream that's at the bottom of the screen that starts with 1, 1, 2, and so forth. This stream induces the frequency vector 5, 3, 1, 0 because there are 5 instances of the number 1 in the stream, 3 instances of the number 2, and 1 instance of the number 3. And of course, 4 does not appear at all in this stream. So the stream induces a frequency vector. And throughout this talk, we'll consider 3 different models, 3 different variants of the stream model, specifically insertion-only stream, where updates can only increase the coordinates of the frequency vector F. We'll also consider the turnstile model, where updates can increase and decrease the coordinates of F. And finally, the strict turnstile model, where updates can increase and decrease the coordinates of F, but all intermediate frequency vectors over the stream are non-negative. We'll also consider the sliding window model, where again, the input is elements of an underlying dataset S, but now only the n most recent updates form the underlying dataset S. And we still want to sample from S using space sublinear in the size of the input. For example, if we only care about the last 8 updates, then as we receive more and more updates, the old updates will expire. And for example, in this stream, only the 8 most recent updates will induce the frequency vector, which is now 4, 2, 2, 0, because only 4 instances of 1 appear in the last 8 updates. So it's clear that the sliding window model emphasizes recent interactions, and thus it's more appropriate for time-sensitive settings. So one problem people frequently consider is the problem of L1 sampling, where the goal is to sample some coordinate I from a universe of size n, which we'll associate with the integers from 1 through n. And we want to sample I with probability proportional to the frequency of the ith coordinate. In particular, we want to sample I with probability the magnitude of Fi over the 1 norm of F. For example, if we have the frequency vector 4220, then we want to output 1 with probability half. We want to output 2 with probability 1/4 because 2 appears 2 times in the stream, and the 1 over of f is 8. So we want to output 2 with probability 2/8, which equals 1/4. Similarly, we want to output 3 with probability 1/4, and we want to output 4 with 0 probability, or never at all, and this is because 4 never appears in the stream. So there's a bunch of previous work for L1 sampling, but most classically, the technique of reservoir sampling performs L1 sampling on a stream, and it works by doing the following. At each time t, reservoir sampling replaces the current sample with the most recent update with probability 1/t. And otherwise, it keeps the old sample, and at the end of the stream, it returns whatever it has. More generally, we can ask about LP sampling, where we want to sample the ith coordinate of the frequency vector with probability proportional to the pth power of the absolute value of the ith coordinate. And as p increases, we can think of more emphasis being placed on the heavier coordinates. So a question that's been considered over the last decade or so is whether this can be done in sublinear space over the streaming model. And actually, it's quite difficult. So the first works considered approximate LP sampling. We're given an accuracy parameter epsilon. The goal was just to sample I with probability proportional to the pth power of the ith coordinate, but we can have some multiplicative error of 1 plus epsilon and additive error of 1 over poly n. So Monmouth-Zaida and Woodruff first gave an approximate LP sampler for p between 1 and 2 using space polynomial and 1 over epsilon and log n. And this is subsequently improved by Andoni, Kraft-Gamer, and Onak, as well as Jawari, Saglam, Tardosh, to get an approximate sampler for p between 0 and 2. And their algorithm uses space that's log squared n, and also a polynomial and 1 over epsilon. Now, simultaneously, Jawari, Saglam, and Tardosh also showed that omega of log squared n is needed for p less than 2, but there's this gap here between the upper and lower bounds of epsilon. So the question for a while was whether this dependency on 1 over epsilon is needed. In particular, we call a perfect sampler if the algorithm outputs a coordinate I with probability proportional to the pth power of fi, but there is no 1 plus epsilon multiplicative error, and there's only an additive error of 1 over poly n. And JR and Woodruff surprisingly showed that the dependency of 1 over epsilon in the previous results was not needed because there exists a perfect sampler for p between 0 and 2 using just space log squared n. So in this work, we ask whether there exists a truly perfect LP sampler where there's not even an additive error of 1 over poly n. More generally, we say that if there's a measure function g, can we sample a coordinate I with probability proportional to g of the number of times that I appears in the frequency vector? So for example, if g of x is equal to the absolute value of x, then this is just L1 sampling. So we want to sample the coordinate I of the universe n with probability proportional to the magnitude of fi. The motivation for truly perfect sampling is that failure probability could lead to biases, which could add up. For example, if we have previous samples that influence future samples, then these biases could really add up. And this is especially cognizant in problems like stochastic gradient descent, where we really want unbiased samples. Similarly, we could have many independent samplers run locally on a disjoint portion of a large database. But then if we accumulate all of these, if we compile all these samples, then the overall distribution could be quite different than the true distribution if each of these independent samples have a small bias. So our results are as follows. We first show a lower bound for turnstile streams. Namely, for a measure function g and a constant r, we show that any approximate g sampler with additive error gamma on a domain of size n on a turnstile stream requires omega of n, comma log 1 over gamma space. And this is even if we're permitted r passes. So the takeaway of this result is that the additive error is inherent on turnstile streams, even for approximate samplers and multiple passes. Our second main result is a framework for insertion-only streams. And we show that there exists a perfect sampler for a measure function g on insertion-only streams of length m using a space that's proportional to log n, but also this quantity zeta m, where zeta is the amount that the measure function can increase whenever the underlying coordinate increases by 1. M, again, is the length of the stream, and f of g is the sum of the measure of all the coordinates of the frequency vector. Similarly, our framework extends to sliding windows, where the space is the same, and again, the expected update time is constant. So our framework can be applied to LP sampling to give a truly perfect LP sampler that uses space roughly n to the 1 minus 1 over p. And recall that our lower bound shows that the truly perfect LP samplers on turnstile streams use omega of n space. So these two results combined show a strong separation for truly perfect LP sampling on turnstile streams versus insertion-only streams. Your framework can also be applied to a number of problems called M estimators. In particular, we obtain polylogarithmic space for when the measure function is the L1, L2 estimator, the Fair estimator, the Huber estimator, or the Tukey estimator. It can also be, our framework can also be adjusted for matrix norms to show that rows of a matrix can be sampled with probability proportional to some measure function. Finally, we show that there exists a truly perfect LP sampling for strict turnstile streams that adapts a truly perfect LP sampler for one pass insertion only streams. So our result converts a insertion only stream perfect LP sampler to a truly perfect sampler on turnstile streams. Sorry, strict turnstile streams. And we get a trade-off for space and the number of passes. So that's our results for arbitrary order models. Now for random order streams, we show that there exists a truly perfect L2 sampler that succeeds with constant probability on an insertion-only stream, and it only uses log squared n space, which is much less than the square root n space that the truly perfect L2 sampler would need to use on an arbitrary order stream. And more generally, we show that there exists a truly perfect LP sampler for p bigger than 2 on insertion-only random order streams. So I'll first talk about our framework for insertion-only streams. And again, we give a framework that outputs a coordinate with probability proportional to g of the frequency of this coordinate, where g is some measure function. So the idea is as follows. We first recall that reservoir sampling samples each element of the stream with probability 1 over m. And here, I mean each update of the stream, not each element of the frequency vector. So each stream update on a stream of length m is sampled with probability 1 over m. So we initialize an instance of reservoir sampling at the beginning of the stream. And now let S be the output of the reservoir sampling algorithm, and let C be the number of times S has appeared since it was initially sampled by the reservoir sampling algorithm. Now, if the measure function can only increase by zeta each time the coordinate increases by 1, then we'll return S with probability equal to the measure function evaluated on C plus 1 minus the measure function valued on C divided by zeta. And here we're going to assume that zeta is bigger than 1. So the probability of that reservoir sampling outputs the jth instance of item I as 1 over m, since there are m updates in the stream. This is the property of reservoir sampling. Now, conditioned on sampling the jth instance of item I, the probability that the algorithm outputs I is this quantity that we said before. And this is because after the jth instance, there can only be fi minus j plus 1 more instances of the stream. Sorry, more instances of the item I in the remainder of the stream. So then the probability that the algorithm outputs item I is 1 over m, because that's the probability that I is sampled, that the particular update is sampled by reservoir sampling. And it's multiplied by the probability that the item is accepted over all instances of the item that appears throughout the stream. So item I appears fi times, and thus we'll take the sum over j equals 1 to fi. And crucially, note that the sum telescopes so that m remains in the denominator, zeta remains in the denominator, but this second term telescopes to just the measure function evaluated on g of f of I. Thus, the probability that the algorithm outputs item I is g of f of I divided by zeta times m. So conditioned on the algorithm outputting coordinate, the probability that the algorithm outputs coordinate I is exactly the measure function evaluated on the frequency of I divided by the sum of the measure function on the other coordinates. So this is great. This means that if the algorithm outputs a coordinate, then it'll output a coordinate from the right distribution. But now how likely is the algorithm to fail, that is, not output anything at all? So the probability that the algorithm fails is roughly the sum of the measure function evaluated on all the coordinates divided by zeta m. So for constant success probability, we can just run zeta m over this fg instances of the algorithm in parallel and take the first instance that succeeds. And more generally, we can extend this to success probability 1 minus delta. So it remains to find out a lower bound, f hat of g on f of g. For example, for truly perfect sampling, we notice that it suffices to find the max coordinate of f times the length of the stream, and we can do this using Mises-Gries with root n buckets to find the max coordinate up to an additive m over root n. And it turns out that this gives roughly root n additive error, and so we actually do need root n sampler instances. Okay, so that's our framework for truly perfect sampling. And I'll conclude this talk by briefly mentioning our lower bounds for turnstile streams. So our reduction is from an informal version of, a version of equality, which is informally described here, where a vector x and a vector y are given to Bob, and each of these vectors are binary vectors of length n. And it's known that any randomized protocol that is able to determine whether x is not equal to y with probability delta must use the minimum of n and log 1 over delta space. Now, if Alice has x and Bob has y and x equals y, then the frequency vector x minus y is the all zeros vector. And so an approximate sampler will not return anything up to this additive error gamma. Thus, the sampler solves equality and uses omega of n and log 1 over gamma space. So this is a bit informal, but it can be formalized, and yeah, we do this in our paper. So in summary, we show that the additive error is inherent on turnstile streams, even for approximate samplers and multiple passes. We also give a framework for truly perfect sampling for both insertion-only streams and citing windows. And again, this shows a separation for truly perfect LP sampling on insertion-only streams and turnstile streams. Our framework can be applied to a number of applications, not just LP sampling, but also matrix norms and M estimators. And finally, we showed that truly perfect LP sampling for one-pass insertion-only streams can be used to achieve similar guarantees for strict turnstile streams with trade-offs between space and number of passes. So thanks for listening to my talk. And I hope that if you have any further interest in this topic, then you'll take a look at our paper. Thanks.